So good morning, everyone. Thank you for coming back again. So last few couple hours with me today. And so I decided, first of all, we had this interruption yesterday, so I'm going to recap a little bit. And then I want to talk more about some practical application of what we have been doing with MD and some machine learning. So, okay, I don't like to, I usually like to move around, but so bear with me here. Okay, so what I want to show you here is just a little bit of recap, right? So we introduced the idea of molecular dynamics. I give you some glimpse into the major inputs and some approximation that you can make and you should not make. If you remember a little bit yesterday from the time step, the approximation in the force field. So those are all things that if you get interested in molecular dynamics and you want to dive in, then you will need to go in more details. But my goal here was to give you some insight on what you should pay attention to. So molecular dynamics, something that looks like this. This is again is for a surface. Okay, you can think of if you are impacting a new surface. So for example, we've been looking at silicon films. Silicon. Yes. So this one. So maybe I'm in the middle, but. What I want to show you, this one was basically an idea that we started also if you're interested, let's say, in new materials. And so this was a nanoparticle of silicon because it has very special electric properties. And so the idea was, can we build some nanomaterials with specific characteristic, right? And so when you develop a model for surface growth, whether it's this or it could be a soot particle, nanoparticles, and those could be acetylene or other compound. Molecular dynamics, as I told you, is now used to describe this process, okay? And so it's not just, a sphere impacting another molecules, but there is way more going on. So something of, you can get insight on the process, the kinetics and the mechanism. So you see something bouncing, you see something that is just laying and stay there, is attaching. Of course, this was an MD without bond breaking and bond making, okay? So it was not a reactive MD. What you see is just if you wanted, the physical interaction between those two. If you add the reactive potential, and you know something about this, I told you yesterday, XFF, for example, then you have a chance also to see if these will bind, forming a covalent bond. Okay, but why this is important? If you want to be accurate again, those are just some of the parameters that I listed if I'm interested in surface reaction, okay? And so impact angle, they have a different energy, different velocity, right? And we talked about this yesterday. So the surface, the curvature, this is flat, but nanoparticle, think about a fullerene, C60, is formed in flames, highly curvature, right? And so that will play a role on those ones. So with molecular dynamics, you can ask all those questions. The goal is usually understand the mechanism, but also translate it to something people can use. And so in this case, for example, if I was asked to work on a project like this, what I will do is run some MD simulation, many MD simulation. You get some trajectories, you get some information. You get information about, for example, how many times they bounce, how many times they stay here, different option that happens. And then you want to analyze the output and try to identify what are the major parameters that give you a different outcome, okay? So do you need, this is important because I'll talk about this in machine learning later. So let's say that you have to define the model here. I gave you, 4 of this, for example, but maybe only 2 are very important. 2 are the dramatic parameters that really change the outcome. So how do you extract knowledge? How do you abstract knowledge from millions of trajectories? This is the next step. Because once you have that information, let's say that is only a function of the impact angle and the curvature. Just give you an example. Then you can write a model that say the rate of reaction of this molecule impacting this surface is only function of impact angle and curvature. You can fit a model to your results. So I'm giving you option for atomistic understanding, but I want you also to leap into the empirical model. Because again, Soot, for example, like a chemkin type, it doesn't care much about this. It cares about a rate. Or what are the species, what are the different importance, yes, but in the end, they want a number. Okay. So let's go to the second step. Yes?
Can you guys see this?
I think it's the light on the, yeah, too much light. Can you see this? Yes. A bit. Yeah.
Can you see that one?
Yeah.
Okay.
Okay. So why we don't do MD all the ways? Because as I show you, the formation of nanoparticles is on the millisecond scale, for example, in some condition. You cannot run MD for a millisecond, okay? So you need to do MD for some stages and then carry the information to the next stage. So why, again, we cannot do MD? Because there are many, many steps. Millions to trillions of steps is a huge computation. And again, I want to remind you that, because I'll show you a solution. They are very much computational intensive because they're dominated by non-bonded pair of atoms, interactions. And so if you have n atoms, we talked a bit about yesterday, then the number of non-bonded terms is n to the square, okay? And then we talk about, can we ignore all of them? So if I am here and this molecule is down there, can I ignore that? So you can, if you're looking at a van der Waals interaction, because the forces fall off quickly with the distance. But if you don't, questions?
How long does it take to run a simulation with MD?
Right. Yes. And I have some data later. So a little bit depend on, so the question is how long it takes usually to run an MD simulation. And so it depends a little bit on the system that you have. So how big is the system? And how also, what kind of box do you need? So yesterday we talked about this. You want the box big because you want to replicate more reality and don't have, problems with the boundary conditions. But also the other issue is that then it's more computationally intensive. So it depends a little bit. We have run simulations of, for example, in liquid water or in gas is a difference also. But depending on the structures, maybe 1,000 of atoms or 10,000 of atoms, you can do for a day. But that's one trajectory. Then you have to do many trajectories to that. And so another point to your question that is a great question is that you cannot give me an answer with one trajectories. You need to do an ensemble average. You have to tell me statistically, if I have millions of reactions, what's happening? So that's the other problem. And so let me show you on this question exactly, because I have more data, but I want to show you the solution that we have done. So here, and so one other thing is the electrostatics. Electrostatics, no, you cannot ignore. So forces fall off slowly with the distance, okay? So if I have a big box, that's better because, for example, for sure I can ignore van der Waals. This atom is so far away from me, but it's computationally more expensive, so you should reduce the box for that. But then you cannot totally neglect some of the forces. So it's always a compromise, okay? Now, I want to show you, I showed this slide yesterday because I want to get here, and maybe this is the point of your question. Is it Chiara? Chiara, right? Oh, Carizza, sorry, I forgot. I tried to learn the names, but I forgot. Okay, so there are many ways to speed up an MD simulation. So you need to be careful, but you need to do that. And so besides those two that I was mentioning yesterday, you reduce the amount of computation per time step, so you have a faster algorithm. Or you reduce the number of steps for the simulation that you need. You say, I don't want to run for 1 microsecond. Why don't we run for 10 nanoseconds? Remember, you need to check convergence also, as I told you yesterday. There are other methods that actually what they do, they reduce the amount of physical time that must be simulated. So what they do is, and I highlighted in red what I want to show you, they make the simulation reach all energy conformational states quickly. So what I told you yesterday is that you need to explore all the landscape. You remember that? You cannot just give me one answer in one valley. You need to go around. You need to explore every possibility and then give me an average if you want. So if you run a simulation, so what happened in the usual, let's see if I can show this. So we are going back here for a second, and we'll show you how the methodology works. So we are here. We created the sum of those pHs that now they start interacting between each other, but also they are growing, remember, with the KMC. So let's look at those interactions more. So the first question that I was asking, and then we get to the problem, is that I have all these pHs that I formed. Some with the gas phase mechanism, like you have seen in Chemkin type, others with the KMC snaps that was, remember, compared with the experience. So you have all this pool of things. Now, the question is, they don't stay there. They interact with each other, okay? And so, especially when you have aromatic, they really attract each other. So how different molecules interact and how the chemical composition and the shape of the molecule influence the interaction. Remember, my goal is to move up in scale. I want a model. I need, as I told you before, for the surface, I want to understand what are the key parameters that affect the growth of those pHs as they move up, okay? And how can we capture this phenomena? So we will revisit later with machine learning, but for the moment, we are going with the molecular dynamics. So I have all this pool of structures. What I am interested in something like this. So I want to put like a bunch of them. We started with the dimers and in a box, and I want to see how they interact with each other. So you see, what they are doing, they are moving also. So you can see something that becomes parallel, they become orthogonal, so this is a lot of interesting behavior. And eventually, what you can do is that if they stay close for a long time, you could also form a bond, okay? So this is all mechanism that I think needs to be clarified as we move up. So what I'm trying is to go beyond molecule 1 plus molecule B becomes C, but having some information. So what did we do for this? We did free energy calculation. Yesterday I gave you the free energy, and I know there was the formula, but the idea is that is a thermodynamic property. So you don't need, with MD you can do a dynamic moving, or you can do thermodynamic property. So it's helping you to tell you the propensity of two things, if you want, in this case, to get together. So the way you read this graph is that you have those two molecules. I just showed you, right? Then you take the center of mass of this, the center of mass of this guy, and you define this distance. If I had a 4 nanometers, those two guys are apart, okay? And then what the free energy is going to tell you is that the energy to bring them together and to form the dimer here, okay? If you push them too close, of course, they will repel each other. But this is what you want to look at. Now, far away, they are apart. Closer is what we want. And this kind of distance between some kind of a peak, the barrier that they need to pass, and down here is related to the rate that we want. So what am I doing here? I'm looking at different pH and define the rate of forming a dimer, okay? So how do we do this? Now, going back to the problem of MD, this is a slow. I have so many compounds, and I need to run for a long time also. I don't want to accelerate. I have to be in specific temperature regime. So I'm not accelerating with 5,000 Kelvin, as I showed you yesterday, some of the simulation. What we need to do is to make sure that I explore the whole landscape. And so usually, if you do a normal MD, let's see if it works. This one should work. This can happen. You know, you are in a valley, and you get stuck here. So you have 10 nanoseconds of MD that you paid a lot of money for, and you're here. It makes sense, because he's trying to get out of this deep valley, and it's okay, it's very stable, but it's not giving you the whole picture. So I need to pass this barrier. I need to go up here, right? So that I can give you a statistical meaning answer. So this is what happens with the normal molecular dynamics. But what we could do, and this is not my movie, so this is a metadynamics. This is an approach that was developed by Lion Parinello. This is 2002 PNAS paper, and the movie was not done by me, but I think it's a fun movie, so I want to show you. The reason why it's fun is because you clearly understand what's going on. So what happened is that you need to explore everything. And so if, in principle, you do something like this that is working, so what metadynamic does is basically adding help to the molecules when they are in the valley. So what they do, after you explore some valley, helps you to get out of the valley, so adding a potential, Gaussian distribution potential to the system. So this is a kind of a picture, a cartoon, but explore this very well. So he already explored this valley. He needs to get out. So they had the potential to push him out, if you want, and then he goes down and jumps down in this other valley, and then speed up the simulations. It is a simplification, but it's an idea. And I think sometimes it's cool to bring back to simple ideas. Sometimes you have a very difficult, complicated process, and something simple could be an answer. So with this metadynamics, that is a very cool approach. And again, if you're interested, there is a lot of mathematics and a lot of knowledge behind that needs to be acquired. But the idea is that helps us speed up the exploration of the landscape, okay? So what happened with us? Let's see, we use molecular dynamic simulations. We also use metadynamics, and we were in exactly the same temperature of the flame. So we started slow for 500 at the beginning, we got 1,000, 1,500. So we never went to extreme temperature. And the first question for us, okay, we have, let's say that I have those 3, 4, 5 compounds. Do they interact with each other? How can I easily describe that? So I have a quick question for you. Let's see, but okay. I give you, say I have 2 molecules, A and B. What is the collision between these molecules? What do you need for the collision between the molecules? I need the mass. What else? So what are you computing? An energy, right? They collide. What is the energy? What's that? Velocity, so what kind of energy is that? Kinetic energy. So usually when you have 2 molecules, A and B, and they say, what is the collision? You look at kinetic energy. So the velocity, they going towards each other, right? And so what they do is to say that the collision between 2 particles, A and B, we usually use a reduced mass, if you remember. And so the common way to define the collision of dimers, so pH in combustion, is to use reduced mass. So you have the kinetic velocity, as you said, and this mass is basically, you have the reduced mass that is a product of the 2 mass divided by the, so you know that, the relative. Okay, what I'm going to show you in the next slide is that this approximation for pHs is not enough. So let's go and look at the first result. So we did 500 Kelvin, so very low. And usually remember, when it's low velocity or low temperature, meaning that things move very slow. So the simulation might take longer. But we wanted to stay at 500. So same graph as I showed you before. This 1.8 is the dimers are far away. Then they get closer, and they found this stable point here, okay? Why this is important? Okay, so this is telling you this is 0. Everything below 0, it means it's a spontaneous process. And so everything from pyrene to those other 3 molecules, they will form a dimer. If you place them at 500, they will form a dimer. Think about liquid. You need to get to liquid eventually, right? So they need to form a bind. So this is a good check. So, but the first thing that you notice here, this is a 4 rings. This is a 5 rings. This is more rings. And this is even more rings, okay? And so the number of rings is not a complete index of stability here. So what you have, look at this. This is a 5, right? And is way more stable than this guy, sorry, this guy that was here. I should have, I don't know why the lines are not there. But so this guy that is the lowest curve here, but anyway, so number of rings is not a parameter that helps me tell, oh, this is the rate of dimerization in combustion, okay? I need something else.
I'm so sorry.
No, please.
Okay, thank you so much. Okay, thank you.
No problem at all. Okay, so what else could be important? Okay, well, look at this now. 1,000 Kelvin. Same picture, now you know what that is. First of all, pyrene. Pyrene, if you place them at 1,000 Kelvin with another pyrene, is not going to form a diamond. There is no way. The line is up here. It is the first one gray. The energy is above zero, right? So pyrene does not form a dimer at 1,000 Kelvin. What happens here, that only these bigger structures, so ovalin and circumcoronin, have the ability to form a dimer in this set, okay? So pyrene is up here, but also this other guy moved up, and the coronin also moved up. So what you say is that the number of rings is not driving this process, or describing the process correctly. What about aliphatic chains? You saw that there was a lot of diversity in pH. So I'm going here result for small molecules. Pyrene, what if we attach this little tail here? And what if the tail has a double bond? Okay. The difference, what do you think is the difference? Why I did these two examples? Any idea? What do you think? Do you have any feeling why double bond and single bond are different? What do you say? Yeah, well, those are two also. And also, so what you call about is so that there is a static hindrance, you know, when they get together. It's not free energy, remember, it's not only about the potential energy, it's also the static hindrance. So if you have something that rotates too much, for example, it will, you know, remove or push away the other molecules. But if you have something that is a little bit more stable or stiff, it's easier for the other one to get closer. So how does the effect of the chains in this one? Same problem here, same free energies. And so what you see here is that now the free energy, this was a 500 Kelvin again. So you have, again, pyrene. This is a smaller scale, okay? This is minus 15. The previous graph was minus 80, I think. So pyrene, okay, is binding. But the idea is that, here, this vinyl pyrene has less static hindrance than this guy. So the single bond can continuously rotate. You give a temperature. Do you remember that the temperature goes in different bonds, and they can do different things, like rotation, vibration, I told you the other day. So what this is telling you is that the type of bond, so the static hindrance plays a role here. And so the flexibility of the chain is important, okay? So the picture gets complicated. It's not just mass here. Then we extended this kind of simulations because we got bigger with KMC, with SNAPs. And now I have also some oxygen, OH. Remember the furane-like compounds in which is oxygen on the 5-member rings. And then those guys that are very interesting. So now the chain is in between. It's not outside. So they rotate. They are not flat molecules. These are very important in the inception and in the growth. So what are the results? And bear with me, I'll try to simplify this graph. So here is the result. Let's go slowly together. So first of all, now I want to talk about the mass. So what I have on the x-axis of those three graphs is mass, molecular mass. I have different temperature. I have a 500, 1,000, and 1680 because this was specific to a flame that we were studying. Okay, so the first thing that I want to show you is that look at those. There are a lot of species that we studied, but look at this Ig. So Ig and IH. Let me see here. So Ig, IH, and IA. Okay. So Ig and is 452, and IA is 448. So they're similar, right? The mass is more or less the same. But if you look at the behavior here of Ig and IA here, and then Ig and IA is not completely the same when you move along the thing. So it's not exactly the same number. Look at the energy on the y-axis, right? So you have the same mass, but the number that you're getting, it's very different. So the propensity of those two species to get together changes with temperature, and even if they have the same mass, the energy is different. And so this must be, the reason why this is happening is because although they have similar masses, the structures and the chemical composition is different. Specifically, this Ig has this guy here that is a rotable bond. So what they do, they rotate all the time. Okay? And so that will create a more static hindrance for two things to get together. IH is a little bit bigger and has a rotable bond, so it really places it on this other side of the scale. Okay, so, but the point is that if you have to describe this process with the mass, this will not be enough. Because, yes, this is a bigger mass, but look at the same mass and you have different results. What about the oxygen? Because we said we find it. We started day one with FT on oxygen. It's important. We added the two snaps. Now we form species with the oxygen. And so a similar process here. I have the free energy on the y-axis, but now on the x-axis, I have the ratio oxygen-carbon. Okay, and so, yes, there are clusters of compounds that you can see. This is 500 and 1,000. What you see is that, so I have IC, ID, and IE here. They have similar mass, 62, 60, okay, which have the same mass and the same OC ratio, 0, 1, 25, okay? But they are less stable than this guy here. Remember, the lower this number, the more stable you are. So this one here in the oval part, basically, somehow the presence of oxygen is influencing the ability of that form a dimer. And so those are the species, IC, ID, and IE. They all have oxygen on this species, while this other guy here, we don't know why, is more stable, okay? Even if the mass is on the same order. So, and similar things you will see when you go up in 1,000 Kelvin. Remember, when you look about, for example, a premixed flames, atmospheric pressure, inception is around 1,200 Kelvin, 1,400 Kelvin. So dimerization plays a role, at least for a while. Or, in other words, it brings pHs together, that then they can react. But you need to know how fast, the rate of those, and which one gets together. So this tells you the ability to get together. So the presence of oxygen destabilizes the dimers. The reason we infer from chemical physics is that possibly because of the increase of repulsive electrostatic interaction of those oxygen present on the structures compared with the pure hydrocarbon, in which oxygen is not present. So now, one slide of a conclusion about this. Why all those results? There was a lot of complexity I need to show because it's too many results. I don't want to get too boring here, but I just show you graphs. The idea, the message is that in general, the dimer state becomes more favorable at lower temperature and lower masses, okay? And the mass alone is not sufficient descriptor of free energy dimerization. So, and in some of the, so the graph here shows this. So if I take reduced mass, that is the concept that you're familiar with, and I plot all my simulation at different temperatures. So blue is a 750, orange is 1,000, and red is the higher temperature. What you see is that for the same reduced mass, let's look here, for example, you can have difference in the free energy that go from here, that is, actually 56 kcal between this guy and this guy here. They can go here, or they can go all the way up here, in which you have a look 20, okay? So same reduced mass gives you a huge span of free energy for dimerization. Again, why we care? Because once we have a free energy, you have a rate. So what this is telling you is that mass is not enough. So if I go back and I say, what is the collision between two pHs, you cannot say reduced mass. You have to tell me something that is a little bit more complicated based on those MD results that you saw before. I got one of these and one of these on were 56 kilojoules. Actually, the difference of 56 kilojoules per mole is for orange. So an orange down here and an orange here. So at the same temperature, that is 1,000, you can have, for the same reduced mass, things that are different by 56 kilojoule mole. That is a lot. Okay. So, great. How do we reconcile all this? So I'm not going to give you an answer right now, but I want you to remember that this is a problem. I need the rate. I need to solve this problem. And so I'm going to continue in a little bit about this when we get to the machine learning. OK, but I want to continue with my MD before we transition. So I use MD, as I said, to get a rate of dimerization because I want to go up in scale. And then can we do something more? So takeaways from this first part is that there are a lot of intertwined properties that I show you some of the results. Some is the shape, rotable bonds, mass, oxygen that influence this dimerization. That is one of the steps, again, for the pH to grow. And they are intertwined, so they have different importance as well as diverse temperature dependence. Okay? Because when I show you this slide here, you can see that the temperature dependent, so you can go from 1,000 to 1,250 to 750, and you can have still a huge difference. So it's not the temperature that brings them together. It's not simply the structures or the oxygen. So they are intertwined, this problem. Sorry, here. OK, and then they have different importance at different temperature dependencies. So mass at the presence of the internal rotable bonds are the most important characteristic that we saw, the common properties, followed by the presence of oxygen and side chain. The shape is a minor role. OK, so mass alone is not sufficient. That's the message. OK, but I want to learn a little bit more. I want to also, as I started those structures, the one also that I show with KMC, with the snaps, how do they get together? So we did the first level with pH. Can we do something similar for the nanoparticles? And so here I have an example of 2 nanoparticles. What happens as my structures go inside? So we did something similar for those bigger structures. So now instead of having like a little pHs, this is 150 carbon atoms, so you're going up a little bit. The problem is that when you go with the bigger structures, MD becomes more demanding, so you cannot do a lot. And so for this, what we did is basically decide to study. I was very much interested in studying a big box of nanoparticles, like really a window into the flame, and run a simulation at the exact flame temperature. And as I told you yesterday, it is a challenge because if you do the dynamic, so we did the free energy right now, but if you do the dynamic, you need to wait. There is a time that you need to rest. And basically, you can do simplification, and I didn't want to go to high temperature, high pressure, and bring them together. So another trick that you can do with MD is to coarse grain the particles. It is, again, some complicated approach, but the idea is that you reduce complexity. So now, instead of having all this information, okay, you decide what are some points in space that can somehow still retain some of the features of the particles, and some of the interaction property also, but still represent the molecules as you move. Okay? So it's reduced complexity somehow, and allow you to run for a longer time. So now instead of having all this guy, for example, so I think this one can be represented by just one sphere, if you want. This guy, you had like 3 wings, for example, so they were more floppy. And so I could not just say this is one ball. I need to at least find 3 sites for this, okay? So you need a little bit of human domain information, knowing that the flapping of these legs, if you want, or arms of this structure is important. You cannot make rigid. Maybe instead, when you have something like this more similar to a Fullerene, it's a buckyball. It could be like one atom, okay? And so you replace this complexity with this, and you need to define or build these forces. So I need to make sure that the forces between this one and this gun somehow reflect the forces between the whole arm of the molecules, okay? So that is all the trick. But we did that, and what you see here are results for MD simulations. I think there were 40 molecules in this. This is first the full dynamic that I could do, okay? And so what you see here is that the type of, so you first do the full atom, MD, okay, before going to coarse graining. So here, what you see, the result of the simulation is that if I have in a box all molecules fully atomistic, that they are rounded like a fullerene, this is the type of blob that you get, okay? If instead in your box, fully atomistic, you place a molecule that look like this, in which there are, floppy arms in this way, then you'd see something different. You see subclusters, right? And the reason is, you know why? Because there is a steric hindrance, because there is a curvature, they move. So the likelihood that they just stick together, it's much lower than having here, okay? Again, what this is telling you is that morphology plays a role in this case. So if I'm going up to primary, those nanoparticles, eventually they turn into soot primary particles, right? And so you get to this blob. Well, the morphology of what I'm building before influence. And so here I have a three scenario, one that I already showed you, one with all floppy, and this is a mixture. This is a mixture 50-50 of round and floppy ones. So again, the answer is not completely is one, but those characteristics like morphology in this case plays a big role, okay? So in this case, it's all aromatic, there is a curvature, they attract each other also. Here there is the entropic contribution is contributing to the result. Okay, so my last result for this section before we move, we'll take a 5 minutes break and then we'll move, is this one. This one I was very proud of. I have to show what I'm proud of. But this was the first simulations. It was done with coarse graining, as I showed you before. And this was, so you can see the formation, I think it's this guy that forms here. This one, they get together, they get bigger. This was the first simulation at flame temperature of 10,000 nanoparticle that we did. And so what we wanted to understand is how those nanoparticles that you just saw, now you have 10,000 of those, how they get together and how they agglomerate. And so you can see the transition from those individual or subclusters to those bigger primary particles for the soot formation. Okay? So again, the idea is that MD can help you with the mechanism, can tell you how the shape, the morphology influence those rates, and also show, the formation of those bigger structures that I thought that was very cool, because this was done at flame temperature. Okay, so the real flame temperature, not an extreme temperature. So this leads you to the formation of primary particle in soot. Okay, so I'm going to, you can see also there is something that is leaving the blob. So you form the blob, but remember, this is all reversible, always. I told you it's very important. So some cases you're forming, but there are places in which you see some detachment also over time. Okay, so main takeaways here, the shape and the chemical composition play a role also in nanoparticle assembly. So before we're talking about pHs, right? Now here I'm looking a little bit more at those nanoparticles going up. And so some predictive models for those materials in flame need to take into account this dependency. And MD is basically something that gives you insight. Then you need to take a leap and get to some more macroscopic properties so that they can be used in empirical models. So what are we going to do next, but we take 5 minutes break here, is we will look at some machine learning, and I will then look at some application in combustion. Specifically, I want to talk about how machine learning can help with the many data, but also how it can help interpreting data. So not just machine learning as a black box, but something that can help us to understand what's happening, okay? And then I will try to expand to nanoscale interaction. So we'll give you some biology and nanomaterials design examples. Any question for me? Yes?
In the MD approach you have, and you consider collisions, do you care about if it's like in coarse graining, like the popular methods, are considering if it's a hard sphere collision where there's no deformment of the molecule itself, or if it's a soft sphere approach where like there is deformment, there is like structure change internally, which might affect the entire internal.
Yeah, this is a great question. So the question is, when you look at the interaction of those nanoparticles, how much the forces basically between them play a role when you do the coarse graining. So great question. So coarse graining has a lot, you can do coarse graining in many, many ways. But one thing that you want to make sure that is that the interaction, this is the reason why we did MD atomistic first. So you collect the forces from MD atomistic, and then you translate into forces between those, for example, three points. So whatever is happening at atomistic level needs to be happening also at the coarse graining scale. So those type of interaction are retained in the forces. Yeah, that's important. So the forces is the most important things because it tells you the dynamic. I needed to make sure they're correct. Yeah. Any other questions? Okay, so let's take a few minutes break, and then we can go in the other topic. So we can come back in a few minutes, 10 minutes. I don't even know what time is it.